Welcome back to another HVAC Engineering-Techie training video. These training videos are intended to be educational in nature and are intended to help you in your career. Today's lesson is on HVAC hydronic systems, basics, and components. So this video we're going to just talk about everything that goes into make up a system, what each of those components do, what their types are, and what the differences are, so you'll understand that. Then, of course, after this video, then you can take the system videos and understand what everything in that system is. So remember, this is the channel that talks all things HVAC. We talk engineering design, construction, equipment, test and balance, controls, efficiency, and performance. So before we start, I'd like to ask you a big favor. If you wouldn't mind becoming a subscribing member if you haven't already. It costs you nothing. It's absolutely free. I'll never bug you. No problems. Just hit the button down below and give me a thumbs up. And the reason for this is Google uses that data to evaluate this video, which keeps me on the air. So I would really appreciate if you do that. It means a lot to me, and I'd say thank you if you do that for me. So let's get started on HVAC hydronic systems, basics, and components. All right, so let's start talking about chill water and hot water systems. Of course, these are just some diagrams of what a real simple cold water, chill water system would be. And in this case, you see we have a chiller here that takes the return water and chills it down, and it comes out to a pump. Pump sucks it out of the chiller and runs it out to coils. All the coils have a control valve, lets it control, and it goes back. And that's a cold water system. The hot water system is similar, a little bit different. It instead of sucking from the boiler, the pump should push to it. Not always that way in design. The reason that's that way is because hot water, if you bring all the hot water in here and if you have 180 degree hot water, you're right near the flash point of the water. So if this is closed off and it's not taking any water for whatever reason, and you have hot water in here, it'll probably flash the steam and erode the impeller. It's really best practice to push through the boiler and push the hot water right out that way instead of having the pump up here. So that's the best way. And this is a hot water system, and of course it still has a coil just like the cold water system, and it circulates the water through the system. This one circulates it this way, this one circulates it this way. So heat always flows from warm to cool. Remember that heat never flows the other way. So hot makes cold things warm, and that's the heat always flows in that direction. Total BTU heat exchange is dependent upon temperature difference, the delta T, flow, GPM, sensible heat of the fluid, and the heat transfer conditions of the heat exchanger. Those are the things that make it efficient, or how much heat it actually transfers. A building chill water system normally have 42 degree to 48 degree chill water set points. It can be different if the engineer is designing it differently, but normally that's the range. So normally set points are 44. A low set point is considered 42. And of course, we're trying to keep this away from 32 degrees where we might freeze a chiller bundle. So we're trying to keep it up a little bit. That's why 42 is about the lower limit. You can get special chillers that will go down to 38. Of course, you have to have antifreeze or brine in the water to do that. Building hot water systems are normally 90 to 180. You can go lower than 90, but that doesn't provide much heat. We don't go much higher than 180 because of getting too close to 212, and we don't want to cause anything to get close to steam. All water systems must be totally full of water and have no air pockets at the high points of the system. If you let air get into these systems, we can actually airlock a coil and it'll stop the flow through the coil, and it causes real erratic heat transfer. When air goes through the coil, it has a much less heating capability or cooling capability of water than of air. And so your thermal transfer goes erratic. If you're trying to pump air through this coil, your heat transfer goes away. So you get all kinds of things. Normally you get noise. So no air in the system. That's really important. Chemical treatment systems are required to limit corrosion and scaling. We don't want this pipe scaling because it can clog the strainers and clog the coils. So we put chemical treatment in to prevent that from happening. Let's talk a little bit about basic water flow. There's two kinds of water flow in pipe. One is laminar flow, where it's very laminar, easy, nice, calm, cool, everything's like that. And then we have turbulent flow, where water's anything but lemon, or it bounces around, twirling circles and all kinds of problems. This basically is quiet. This is noisy. We don't normally ever want this, but every once in a while we do. So we want nice sound. This is lowest possible pressure loss in the pipe. This is pressure. There's only one condition we ever want this condition. That's inside of chiller tubes, because this actually transfers a lot more heat than this does. And the reason is these layers kind of insulate the next layer. So this layer here sees the heat of the wall of the pipe, but the next one kind of insulates it. So that's why with this area, they all see the wall of the pipe because they're all turbulent flow. Okay, now talk about entrained air. This is what we want. We want perfectly no bubbles, no water. That's what we'd like to have. Doesn't have it all the time, and this is called bubble flow, where we get little bubbles in it. And these are coming in from leaks in valve stems, leaks in pump seals, anywhere that air can touch. We get these little bubbles. And then this is called saturated wavy flow. This is called plug flow. And what this is where all the bubbles have got together and formed air pockets in the pipe. And this is what will drive you crazy, because if this gets in a coil, it's not transferring the heat it should be. And this is a little worse. This is where you've got plugs of water flowing down the pipe. And this one will drive you crazy as a test and balance guy, because when it's here, you look good. When it's here, you don't look good at all. So it still has a heat transfer problem. And this also can cause water hammer, because if these plugs get moving down the pipe, they can actually cause water hammer in the pipe. So erratic flow, we don't want that. Sound. Pump curves. Remember that we are judging how much water we have in a system, either by flow meters or by reading a pump curve. And these pump curves, this is the head reading over here, which is normally in feet. It could be in PSI, but normally it's in feet. And then we have the GPM flow down here. So if you come and you got a pump design, and you got this GPM there, which I think is a 500 GPM, and you go up to a pump curve, say like you're going to have it right here, which is at 70 foot of head, then that's where it'll be operating on this curve. So it'll be that particular curve. So this is the impeller diameter, and these are all impeller dimensions here. So that's how you read a pump curve, and these are efficiency curves. So we're always trying to select a pump right in these high efficiency areas and not out here in the low efficiency areas, because that matters how much horsepower it takes to pump the water around. This is a really bad curve. I don't know where I found this, but you don't see pumps like this almost very often. The problem here is you'll see this curved line here. This is the impeller. It actually slopes back down here, and what that means, you should never select a pump this way. What it means is that the pump, you draw a straight line across there, you see there's 2 points on this curve, which it means if you're at that head position, this pump can vacillate between that low flow and this high flow, just back and forth, and you never know what's going to happen. So that means the chill water system might have this flow, which I think right here is 80 GPM, might go down to 20 GPM, back and forth, back and forth, back and forth. So we always never want to select a pump that'll operate in this piece of the curve. If you have a curve that slopes back down, never ever a pump should ever be selected in that area. If it is, then you got to figure out some way, and I don't know how you'll do it. If it's because if it'll hit both places and you're right in here, it's going to flop back and forth. You have no choice. The only way it works is if you're over here like this. So this is a really terrible curve. I don't know where they found this curve, but anyway, I did find it for you. And again, this is just like in the other things we talked about on air. We have parallel fans or series fans. It's the same way with pumps. Water's the same way. If you have more than one pump, this is the first pump curve right here. This is the second pump curve here. If you have 3, this is the third pump curve. So the standard within the industry is if you have 2 pumps, you have 3 pumps. If you just have 2 pumps, you don't have a third one, then we assume that 1 is the load and 2 is a standby, 100% standby. Maybe a bad assumption. So you may have to actually add up all the loads to see what the deal is. If you add up all the loads and the loads are twice this pump, then it takes 2 pumps to run for the load, and the third one is standby. You should never have something that runs 3 pumps together, but you don't know. So whatever the design is. So each of these pump curves are like this. So if you have pump 1, it curve comes down to right here, and this is the flow at no head, at free flow, and then this piece right here is exactly equal. P1 is equal to P2 if it's got no head. But the minute you put head in it, you notice these are curves. So if you're up here, you'll notice this one right here is the flow, and this one right here is the flow. Well, the deal is this second pump only provides about 80% of the flow of the first pump. So as you get 3 together, see, this one's probably 35% less than the first pump. So you don't get, when you have parallel pumps, you don't get twice the flow if you run 2 pumps. You get something less. It's kind of important to know. And same with series pumps. If you stack them up and have series, the second pump doesn't quite give you double the head. It gives you something less. So that's the 2 you could have in a system. Hydronic components, we're going to talk about chillers. We're going to talk about cooling towers. Talk about pumps. We're going to talk about coils. We're going to talk about boilers. We're going to talk about heat exchangers, surge and thermal storage tanks. We're going to talk about water treatment. So here we go. Let's talk about chillers. There's all kinds of different kinds of chillers, and I'll try to go through and explain why they select the different kinds of chillers. This is a scroll or reciprocating compressor chiller, and these are small chillers, so we can get these clear down to 5 tons. So this would normally be a 20-ton chiller, or a 40-ton or 50-ton chiller would be in this kind of range. Small capacity, multiple compressors. So you have multiple compressors on here. So there's stages. So we got 2 stages. Now, if these are digital scrolls, it'll be modulating. So they could be scroll compressors or they could be reciprocating compressors. Digital scroll means it's modulating, and I'll talk about that in the refrigeration when we talk a lot about what a scroll and a digital scroll is. Reciprocating compressor chiller. These are chillers that have these semi-hermetic compressors. So they have a compressor and have a motor built into it, and the motor is exposed to the refrigerant flow. That's why it's called an enclosed chiller. So you can see that compressor, and the compressor here has, let's go back here. This compressor here has, normally they have unloaders on the heads. So this is a row of heads, this is a row of heads, and there's one on the other side. And they put okay, we're going to start chillers over. All right, starting chillers over. So now we're talking about chillers. We're going to look at chillers. First one is a scroll compressor chiller or a reciprocating compressor, and these have just normal compressors on them. And these are small chillers. These are small compressors, so they might be 20-ton, 30-ton, 40-ton. They're small load, have multiple compressors. So the multiple compressors can actually stage. So this one, if it had 2 compressors, it would have 2 stages. Or they could be digital scrolls, so they're actually modulating, or they could have VFDs on them modulating. Next is a reciprocating compressor chiller. This has got the chiller bundle, the condenser bundle down here, and they have these reciprocating compressors. These are semi-hermetic compressors, and they're called semi-hermetic because you can actually work on the heads. You can work on the valve plates without actually opening the refrigerant circuit. Now, the refrigerant actually cools the motor, so the motor's inside the compressor. These are small capacity, multiple compressor, nice small. These could be 50-ton compressors, so you can have a 100-ton chiller, maybe a 125-ton chiller. They can have more than 2 compressors. So these are ones we used to use a lot. We don't quite use these much anymore because we have better opportunities to use a little better type chiller. Screw compressor chiller. Screw compressors basically have a screw system on there, and it has an inlet valve that actually can modulate, so you can modulate the load. And these are you can actually speed them up because they are solid. They do move the refrigerant through these veins they have in here. So these can be a little bit larger. These could be up to 250. The screw compressor can go to 250 tons, something like that. And then we have centrifugal compressors, which can be large chillers. These can go up to 2,000 tons or a lot, quite a bit. Normally 1,000 ton is the sweet spot for this chiller, or anything below. And these go from 100 ton up. And of course they have a centrifugal compressor. It looks like a jet engine basically, and it sucks the refrigerant from the evaporator, and it pushes it through, it sucks through into the condenser. and evaporator. So we have a water-cooled condenser and a water-cooled evaporator on the machine. And these, like I said, can be quite large, and they can be multiple compressors also. You can have, I've seen them, 2,000-ton chillers that have two 1,000-ton compressors on them. They also make these with new magnetic bearing chiller compressors, which run about 30,000 RPM, and those are highly efficient. And there's a couple manufacturers that manufacture those nowadays. And then there's absorption chillers. Absorption chillers are not used very often. They're a real pain to keep operating well, but they basically are gas-fired, steam-fired, or waste heat absorption systems. And what they do is they take heat from some source and put it in, and it actually heats an absorption material and runs it between that two stages, and we have condensed water coming in to cool it, and it actually produces a cooling effect by the absorption of this material that's inside the chiller. So these, not a lot of people are trained to operate on these, and the only problem we ever had with these is if you let your condenser water get away from you, you can actually freeze up the refrigerant inside these things. What did I do here? The refrigerant inside these things will actually solidify. We call it freezing up. They're not actually frozen, but because of their chemical deal is not like water, they will actually turn into a solid. To fix it, you have to have a service guy come in and heat this stuff up high enough to melt it back again. And once it's liquid again, then you can continue the operation. So a little bit of a special service on absorbers, but where they're really used is with waste heat. If you have a lot of waste heat below 180 degrees or above 180 degrees, you can actually use that hot water to actually generate air conditioning. I've used them on solar systems where we had solar oil coming in, and that is the heat source. Nowadays, most is gas, and it has gas burners in it, or else it uses steam. Waste steam is a really good use. If you have a big industrial facility and you have a lot of waste steam, then you can make all the air conditioning with these. So that's really good. All the chill water you can make with an absorber. And then, of course, we have air-cooled chillers, and air-cooled chillers can be any of these up here. They can, it can be a scroll chiller, it can be a reciprocating, it can be a screw, or it can be a centrifugal. And it's just, instead of having a condenser bundle, it only has an evaporator bundle, and it has coils and fans up here as a condensing unit. The limitation of these, of course, is they don't work very well in high ambience. If you have a high ambient of 110, 115 degrees, these are not your best choice. You need to have a water-cooled system. That's the only problem. Now, if you live up north where it never gets above 90 degrees, these are really a nice choice, and they're mainly used there. All right, cooling towers. So cooling towers come in many different types and shapes and sizes. So this is called an induced counterflow. And this is probably the most common one you'll get on HVAC systems. Power plant's a different story, bigger job. But anyway, so these towers basically have a basin, a water basin in the bottom, and they have a distribution basin on top, and then they have fill that actually fills below this section right here is a section of fill. And this fill actually lets water flow down around it, and it wets the surface. And then as you pump air through this fan out here, it sucks in the side here, and it turns 90 degrees and goes through this fill, and that water on the outside of the fill evaporates, causing an evaporation effect, thus cooling the water. So basically the hot water from the chiller comes back in here, and the colder water comes out here and goes to the condenser barrel in the chiller to cool it. And those are called induced counterflow. These can be, up to maybe 500 tons, maybe 600-700 tons, and it can be small also. All right, so now this is a induced cross flow, and this can be a big tower. These towers here can be used on power plants, all kinds of places. So these can be quite large. These can be 2,000 or 3,000 tons alone, or they can be down to maybe a couple hundred tons. But these are a more expensive tower than the other side, so these are why these are not used drastically in air conditioning. So this flow here basically goes through this way, and this is the fill on these towers, and this fill, the water pumped back from the chiller is hot, and it comes across in these pans. The pans let it flow through the fill back into the basin, and then the air comes in through these slots, these louver slots, and then is induced up by this fan. These are big units, and this fan can be they're all propeller fans, but this could be a gear fan where there's a big motor and a gear drive to turn this direction, or it can be belt drive. Nowadays, it can also be VFD drives, so they could be that. Now, almost all towers nowadays will have a VFD on the motor because it's plumb simple energy savings. And I used to calculate every tower I modified with a VFD and had all these calculations. But after a while, I said, why am I doing this? Because every one of them show they pay back in 3 to 4 months. So there was no need to do that calculation to prove to an owner it's going to save energy. It's going to, every one I've ever done pays back in 3 or 4 months. So you need to put a VFD on that. This is what we call a fluid cooler, and a fluid cooler is basically a regular tower, and it has a water basin on the bottom that has a pump, and the pump pumps this water out up and over the fill. This is the fill, tower fill, and as the water comes through that tower fill, the air being coming up cools the water and gives an evaporation effect so the water gets cold. It then flows across this heat exchanger bundle and wets the bundle, thus removing the heat from the condenser water. So this heat exchanger right here has another water stream going through it, and these are used to serve things like water-cooled package equipment, hydronic heat pump, or a process. If you have a process, I've had these where we've cooled laser beams and stuff like that, but that you don't want this water exposed to the cooling tower water, because this water is dirty. It's hard to keep clean. It has a lot of issues, and you don't want to try to clog any small heat exchangers, so they use this separation of the two. So this has 2 fans or 1 fan or whatever, and so these are sized between, these would go down to 25 ton up to 500 ton or so, and beyond that you start using multiple towers. And the reason I don't use these everywhere is because, 1, they're expensive because of this heat exchanger runs this price way up, and 2, these don't last forever because a normal cooling tower will last 20, 25 years, not too much beyond that, unless it's a hand-built-up tower. But these have a problem in that if you have a very small bunch of water. You may have down to 200 gallons, not much in a fluid cooler, which when things go awry, it can go fast. When in a regular cooling tower, you may have 1,000 gallons or 10,000 gallons of water moving in the condenser barrel, so it changes slowly. These can change very, very quickly, and so sometimes the chemical treatment systems are not real robust on these, and so you can get some chemical treatment problems, which then can negate this tower. We've seen these last 7 or 8 years, and they are expensive. So another way you can do this is you can actually put the heat exchanger out here in a flat plate heat exchanger and put some pumps. It seems like it'd be more expensive, but number 1, it's 30% less operating cost. This heat exchanger and the fill adds more air resistance. So these towers are not as efficient. These fluid coolers are not as efficient as a tower. So you can save some money by putting a separate heat exchanger. Thus, you just use regular towers, so that's less expensive. Evaporative condenser is exactly the same thing as a fluid cooler, except here we have a refrigerant circuit. So we have hot refrigerant coming in, and these are used in places like supermarkets and places that have cold boxes and freezer boxes, and they have several circuits in one evaporative condenser. So they can run 3 or 4 different refrigerant circuits in these tubes. And everything else about this evaporative condenser is exactly like a fluid cooler, except instead of water to water, we got refrigerant to water cooling. Same problem. These you can't use a heat exchanger out here because it's refrigerant direct into there. But when these start scaling up, they're really expensive, so you have to be careful with that too. And then we have dry coolers, and dry coolers have condenser water flowing through them, and they just have air. And these are designed for cold climates. If you have a climate where the maximum summer temperature is 78 degrees, you can probably do most of the cooling right directly with air cool. So this makes it an air cooled system, except it's just a dry cooler. And a lot of times we use these in buildings where they have need to run the chiller in the wintertime, and it's cold outside, so these make excellent condensers, and they're real cheap, right? There's no water to them, and airflow is not this critical because we have really cold air. You might have 20-degree air out there and you're cooling it with that, so you have to modulate these fans down to not have that much air. So these are very effective. Now in my town, we don't have these at all. I mean, because our our coldest winter day is 65 degrees or something. So are not used here because it's too warm. A cold climate cooler basically is what those are. Okay, now let's talk about pumps. Different kinds of pumps used for different purposes, but namely it's design choice. And the first one we'll look at is an end centrifugal base mounted pump. And this is the normal standard pump. And the reason these are popular is because you can change a motor without fooling with the pump, right? So you got a coupler, and if you have a burnout motor or a bad motor, you take it off, put a new one on, and you never have to open the system. And they're efficient. They're pretty well the standard of our pumping industry. Then we have close coupled, which the motor is actually mounted on the pump. So to actually take the motor off, you have to take the pump out. You have to take the water system apart to be able to get this. These are cheaper, of course, but any real user that's maintenance oriented would never use one of these because it costs more to work on a motor than it does anything else. So the close coupled, and then we have vertical inline, and this is an inline pump that has a motor connected right now. It's essentially like that close coupled pump. To actually work on this motor, you got to actually open the pump because the shaft is bolted to the impeller, so you have to take the impeller off to do that. So you have to open the circuit. Now these are designed similar sizes to the other pumps, the base mounted and the close coupled, except they're vertical, and it's a space-saving thing. You can put a fairly large pump in a very small space, whereas the other one has to have that long leaded area, plus maintenance area all the way around it. Then we have a split case. Now, split case, the regular pumps, these like this, these regular pumps are centrifugal pumps that basically are used for low flow, high flow, low pressure, high pressure. So those you can just do pretty much anything with. These split cases are designed to move more water at lower head, but they can move a lot of water. I mean, you can get these in 24-inch sizes, pump a lot of water, but normally not up to the same head level we would have in suction centrifugal pump. These are designed that the actual case splits open, so if you need to work on it, you take the whole top of the pump off, and then it has a connector and motor. This one you can still work on the motor without opening the pump. Then you could get vertical split case, which is the same thing, but it's vertical. Now this one you can actually change a motor because it's got a coupling here. So these are, again, because of save space, it's still a split. Now I should mention on these, the impellers actually split. The water coming in this pump, it actually has an inlet on each side. It's like a double inlet fan. It's got double into the water, and then the impeller pushes out this one exit. That's why it moves a whole bunch of water, because it's got two inlets. It's much easier to inlet than its end section centrifugal. This one's the same. It has the same thing. It has two inlets. The water coming in flows around. I guess it's this way. The water flows in this way, and it flows in this way, and then this is the volute, and it comes out this way, right that way. So that's a vertical split case pump. Now these are specialty pumps. This is a multiple stage high pressure. If you need really high pressure, you can get a pump with lots of stages. I've seen these clear to 8 or 9 or 10 stages. The biggest one I ever did was a mine where we had to pump the water 1,500 feet, and it was a 11 stage centrifugal pump. Number one, really, really expensive. Number two, the suction comes in here. This impeller boosted up so much, and this impeller boosted up so much, and this one boosted up, and this one boosted up, and that's the way they work. They're high pressure by having multiple stages in series. Then you have vertical turbine pumps, and these are like well pumps, but we use them in cooling tower basins. So basically they have multiple impellers in series, just like that last pump, and these will pump it up and then take it out to the condensers, the cooling towers we need. So those are vertical turbine pumps. Then we have circulator pumps. Circulator pumps are designed for domestic hot water systems or really small flows, and these are inline in a pipeline with small motor. These are normally between 1/2 inch and 3-inch. Nowadays they are making some big ones that set vertical, and you can get big pumps. The problem with these is the mountings are always complex because the pipe supports some of it, but if you have a big motor, the best practice is to support the motor separately. All right, coils. Coils, we have lots of different coils used for. Chill water coils. Now, chill water coils are basically a duct frame with tubes going through the coil, copper tubes with aluminum fins, and the fins are there to give it lots of area to transfer heat. These are available with different rows. You can see that what happens here is the water comes in, and it goes through this row, and then it goes back that row, then it comes back to this row, that row. So that's the way to get water around it. It serpentines through this coil, and then it comes out on the return header. And these are available 1 to 10 rows. Normal is 1 to 8 rows. Normally for chill water, it'd be 4 to 8 rows maybe. And that the number of rows detect how much heat you're going to transfer, along with the fin spacing. And fin spacing can be from 8 to 24. I think I have it in here. It's 1 to 10 row for chill water, 6 to 24 fins per inch. Now, I don't know why the manufacturers do this. You should never use a 24 fin coil. And the reason is you can't clean it. So what happens when these get dirty, a technician has to come here and clean this coil. And the way he does that is he sprays water and foam on this. And this foam is designed to expand its way through the coil and push the dirt out the other side. And then he takes a hose and he sprays water, not a pressure washer because that damages the fins, just a regular hose, and blows water through there to get it clean. Well, if you have these really 24 fins per inch, they're so small that the dirt just impacts it. We can't push the dirt out of the coil. So that's why 24 fin we shouldn't use. Now, why did they make it? Because they transfer a whole bunch more heat. I mean, because you have twice the surface area, so you move a bunch more heat, and they're cheaper. So that's why they use them, but you shouldn't. I've always, on my commissioning jobs, restrict fins to 12 fin. I'd like to have 10. 10 is really good to clean. 12, but over 12, you don't need them. Now, sometimes on a reheat coil, maybe they'll go to 18, but never 24. I don't know why the manufacturers even make them. Then we have hot water coils that are exactly the same, except they're smaller, 1 to 6 row. And the reason is because we have much higher temperature water, so we get a greater delta T, so we can do a whole bunch of heating with a 4-row coil. Most reheat coils are only 2-row. So on the chill water side, though, we don't have that large delta T, a small delta T, and we have a wet coil. Because when the cold water is colder than the dew point of the air, it will suck moisture, and the coil become wet and drain down to the condensate pan. So, but for hot water, it has a 6 to 24 fin, but remember, just because you can, you shouldn't. At 24, you shouldn't be going there. We can have multiple coils. These are stacked coils, and these coils, because really large coils are hard to handle, so they may, if it's an 8-foot high air handler, and they might have a 4-foot coil here and a 4-foot coil here, and they have separate pans, or they may not. This top coil may drain down on this coil. They can do either way. These are series coils, where they have one coil on another coil. Now, the only reason you'd ever use these for chill water anyway is that you need a lot more capacity than one coil would give you. Say if you needed 18 rows, you can't get it in a coil, you're going to have to go to 2. Or you might have some reason you're staging them. Who knows with the designer, but it is possible to see them this way. And you can have counterflow is important. So this is one thing that is the most important for chill water coils. You must, absolutely must, enter the coldest water on the leaving air side of the coil. So as the air comes through this coil and hot air enters and starts interacting with the cold water, it will start lowering the temperature. There's my mouse. It will start lowering the temperature in the coil till it gets to here. At this point, it will see the coldest entering water, and so it'll make the coil at this point the coldest it's going to be in this entire coil, and will dehumidify the air and it'll start bringing out the moisture in the coil. If you pipe it the other way, where this is return water and this is supply water with the coldest water here, what happens is the water comes in, it sees that real cold coil. That's great, so it drops. But now when it enters this, it's now seeing return water, which may be 10 to 15 degrees hotter, and it will never dehumidify the air. So basically, they will not work if you pipe them backwards, where the coldest water is on the entering side of the coil, air side of the coil, and not the leaving side. It's in commissioning, we check that all the time, and about 10 or 15% of the times we find them piped wrong, which means the coil doesn't move the capacity it's supposed to move. So counterflow is really, really important on chill water coils. On hot water coils, it's not as important, but actually the same principle applies. We just don't need it for water removal. So what I always taught my installation technicians is just always pipe all water coils with the supply water on the downstream leaving side. Then you'll never be wrong. Hot water coils doesn't matter too much, but it does increase the capacity of the coil. So why would you not do that? It's just the way it should be in design. All right, hot water boilers. Since we're in water systems, we got hot water boilers. So there's all kinds of different boilers, and they operate slightly different. This is a hot water, it can be gas or oil fired, and this is a water tube boiler. So it's a boiler that's built with a water tank down below, and it's got pipes that take the water up to the hot water tank on top. And these are normally in a circular round configuration. So in the middle is a flame box, and so the burner here blows a flame down through this box, heating these pipes, and then the air exits at the end of the boiler, and it comes up and goes out the flue, and the hot water is ejected here. So we have cold water pumped in here, and it goes through the tubes and out to this pipe here, and that's called a water tube boiler. Now, water tube boilers we normally use are small boilers in HVAC, but they can be big, because all huge boilers are water tube boilers. All boilers for power plants and things like that, that'd be thousands and thousands of tons of heat, boiler horsepower, all use water tube because they're easier to build. You couldn't build a fire tube effectively in that size. So even though we use these for smaller boilers, in the industry they could be really, really large boilers. The only problem with these boilers is that this water temperature here must leave the boiler at a certain temperature to prevent condensation on the boiler tubes. So normally it's something like 130 to 138 degrees. So when you set these boilers up, they must never allow that colder water to leave the boiler, because it'll condense, and that'll rust these tubes and it'll destroy the boiler. I've seen brand new boilers be destroyed within 3 months because they didn't have them set. They were doing 120 degree water or something that's cold, and that should not take place. Small to medium capacity, even though they make them in huge capacity. And this is what's called a fire tube boiler. And this is the one we use for our little larger projects. Like if you have 750 horsepower, 1,000 horsepower, we'd use this kind of boiler, fire tube boiler. And a fire tube has tubes again, but they're not filled with water. In the last boiler, the water tube boiler, the tubes are filled with water and the gas is on the outside. On this one, the tubes are filled with a hot gas and the water's in a bundle, or is in the receiver around the tubes. So here we have this fire box goes down and comes up into this plenum, and it's got tubes, fire tubes that run to this side. So this pushes and this heats these fire tubes, and this starts heating the water up in this vessel, and then it exits the flue, and then the hot water, cold water is pumped in down here. It is around this vessel as it heats up, and it pumps it out. So this one is not susceptible to the rust problem that the water tube is, because these are always embedded in water anyway, so it doesn't matter to this one. A medium to large capacity for HVAC. Gas or oil-fired cast iron sectional. Okay, now cast iron sectional are a traditional boiler. We used to have these everywhere, especially in homes when they had steam in homes. So you see here that you have on these, they have these big sections, big heavy cast iron sections. They're vertical boxes with a hole in the middle that runs down. In other words, inside of here, the water has a vessel, kind of like an engine block, where the steel is around it, and it's got holes or channels inside of it where the water mixes and goes through. And they're gasketed together so the water can go together. So at the bottom of it, we have the cold water is pumped in the bottom, and they're connected at the bottom. And then as the water heats it as it goes up here, and then it's connected again into this hot water tank, and it goes out. So this one becomes much like the fire tube, except it's not got fire tube. The fire's in these cast iron sectionals. And the reason these work good is the cast iron absorbs a lot of heat. So once you get one of these hot, you don't have a lot of flame variation because these retain heat in this cast iron, which then actually heats the water. So in this one, the fire goes down the middle and out around and goes out the flue, and then the water goes out this way. These are also in a situation where you don't have to worry about that leaving temperature. Well, you might on this tank, but it's not like a fire tube, which the tubes are always in water. These always have water on the inside. They have nothing on the outside. So this we probably need to control the temperature like we do on the water tube. These, and the only thing a problem about these are really expensive because the cast iron is expensive and they are heavy. And these are normally built up on site. So you get the boiler frame and then you have to load these in one at a time and hook them together. On a smaller one, they'll become as a compact unit, but a bigger one of any size, you have to put them together because they're heavy. Gas-fired condensing. Okay, now a condensing boiler takes advantage of that condensation of temperature difference, and it actually uses that heat to preheat the water. So these are more efficient. Normal boilers, like all these other classes, are probably operating at 80% efficiency. These will operate up to 95% efficiency. However, there's one problem with these, and people don't realize. Designers like them because they're energy efficient, they design them, but what they don't realize is if the split is not large. So like if you have condenser hot water returning that's hot, these won't condense, so they're not efficient anymore. They go back to being an 80% boiler just like everybody else. So they normally need a 10 to 14 degree difference, and if they don't, they're not going to condense, so they don't become efficient. So that's a problem. They specify and buy condensing boilers thinking they're going to give them this efficiency. They end up not because they're not being controlled correctly. Needs entering water temp, needs a low watering temp. If it's high water temp return, they won't condense. Then we have electric boilers, which are going to become a lot more popular with what the industry is trying to do to electrify everything. And the problem with electric boilers, of course, they use a lot of energy. It's the least efficient of any of the boiler. 80%? No, would be way lower than that. So these basically just have a control system and a large heater elements inside these tanks to heat this water. Stage electric heat elements, so they have more than one stage, mainly because of the problem with induction current, having too much current in one large thing. So these are electrical boilers. Heat exchangers. Okay, they got shell and tube. Now shell and tube basically have a hot fluid and a cold fluid. So basically normally they're steam, or they might be hot water to hot water, but normally they're steam to hot water where the water's running the tubes and the steam is in the barrel. It's called shell and tube, small to large capacity, high pressure. Got plate and frame heat exchangers, which basically have these plates with grooves on them. And what happens is these grooves direct the water so that the water runs like this down to the outlet, and then the processed water runs this way down to the outlet, and they transfer heat through these stainless steel plates. These are low pressure, very efficient, but they won't take really high pressure because these are designed to be cleaned. These were originally designed to be pasteurizers and dairies for milk. So every day they had to take them apart and clean it. So what they do is you unscrew these bolts and pull this back plate off, and then these plates can come loose. You can take them off and wash them and put them back. However, these plates are not like the old milk plates. Their gaskets aren't really made to be taken apart every day. But you can take them apart to clean them, but it's a job. I've had guys work on these. It take two guys an entire day to just put one back together. And the reason is you may have to compress this thing, from being 4 foot when you put all the plates in and put the big, you're 4 foot, and you really need to be at 2 foot so it doesn't leak. So you have to bolt this down and compress this plate, and it takes a lot of time. You wear out a couple of guys doing it also. But these also have low pressure drop. They can be in the means of 5 to 6, 7 psi drop, which is small for a heat exchanger, and have a very small footprint. Then we have welded plate, flat plate exchangers. These are for small loads, like we use these a lot for sidewalk snow melting and things like that, where we have small loads, and We use them. These are not too cleanable. You have to clean them with acid. You can't get in to clean them. They don't come apart. But they're cheap, they're inexpensive. Now these heat exchangers here, we'll use these for normal heat exchanger application, but also for chiller economization. So we can put these in a chill water system, and it can take the place of a chiller when we have colder temperatures outside. Have about the same pressure drop as a chiller bundle. So now tanks, a lot of different tanks we use in HVAC. These are expansion tanks. This is a traditional one, which was a horizontal tank that was just a tank, and you put in an air charge. So the upper 10% of this tank was air. And then the water come in, and the only problem with these is eventually the water would absorb the air, and now you no longer had expansion. And this is designed to let the water change temperature so it can expand and contract without raising the pressure of the water. And then we have vertical ballast tanks. These are expansion tanks again, but have a rubber bladder. And what they do is you put the pressure you want of the water in the bladder, and it allows the water to change pressure by squeezing on the bladder. And these are what most everybody uses today. They're nice. You don't have to worry about the expansion tank unless the bladder breaks, and then you have a problem. You got to fix it. But pressurized, non-pressurized, so these are the pressurized type we use. Surge tanks. Now, expansion tanks can be quite large. These are ground-mounted ones. Normally, these tanks run from 40 gallon, 80 gallon to a couple hundred gallons, and you size these by how much expansion you think is going to be in your system. So your designer needs to select these tanks. Surge tanks are to prevent the system from surging, as the name, but what it means is, like, if you have a chiller, if you have a small chiller and it only has 1 or 2 loads on it, you're going to have a problem, because the loads are going to come on, the chiller needs to come on, the loads go off, now the chiller needs to go off. Well, that doesn't work very well. You can't turn the chiller on and off all the time, because it needs to put load into that water, and it doesn't have time to do that on and off. It's called surging. So we put a tank in here, and all we're trying to do is increase the capacity of the water. So instead of it only having maybe 400 or 500 gallons or maybe 200 gallons of chill water in the entire system, this could be a 400, 500 gallon tank. So now the chiller comes on, it's got a larger mass of water to cool, so it can stay on longer and not go on and off, on and off. That's what surge tanks are. Small number of loads. And we have thermal storage, and thermal storage could be above ground energy storage tanks, which are big tanks that are insulated that we can store the cold water in. And these can be open or can be below ground. And these are normally open tanks, whereas there's an atmosphere pressure on the inside of it. So normally, remember, our chill water and hot water, we don't store hot water. The chill water systems are basically pressure vessels, right? Well, when you go into one of these tanks, it's no longer a pressure vessel. This introduces a whole complex bunch of problems, because when you pipe this water from the system in here, it becomes open system, and you have to suck it out of here because you can no longer pressurize this, and you have pumps to suck it out of here. Well, this is now an atmospheric system, so you have to be careful with that, of how you manage the pressure within the system becomes complex, and water treatment becomes a lot more complex. Now, these tanks are normally quite large. The biggest one I had was 1.5 million gallons for a university. I put another one in at 350,000 gallons. And for thermal storage, these are, besides the complex problem of the pressure, the rest is easy, because it's got a fairly good stratification of temperature in the tank. We know exactly how to do it. Ice is much more difficult. This water was pretty simple, and that's why this university has 1.5 million gallons. And they use it to shave off the peak load in the afternoon for their energy savings. And then you can have closed pressurized tanks. And a lot of people just put a bunch of tanks in a building that are pressure vessels and pipe chill water. But that also works. These tanks are somewhat expensive. So I've actually never done one like this, but you can certainly do pressurized tanks for chill water storage. Water treatment systems. All right, we're going to talk about water treatment now. Water treatment basically on the closed loop, which is where the pump pumps through the evaporator and pumps out to the coils, through the coils and back to the pump. And this is what this closed water system is. Now for the closed water system, what we have to do is clean this pipe. So when it's all done, we'll take and put water in and run it for a period, and then dump that, fill it with water again, and put a detergent in it, soap in it, basically, to clean all the pipe, clean the oil out of it, clean the cutting fluids, anything that's inside this pipe out. Then we dump that. Then we flush it a couple of times with clean water. Then we fill it again with clean water, and then we put passivation chemical in here, which may be molybdenite, may be a nitrate. It could be whatever chemical the chemical guy is going to use. And its intention is to coat the inside of the pipe with a passivation material to keep it from rusting. And the way they do that is they put it in through a pot feeder. Now, a pot feeder is a small tank. It's a pot feeder that's actually piped around the pump. So the pump is small pipe, 3/4 inch. So it's running water around there to dissolve whatever you put in here to get it inside of this. And if you need to put a whole bunch in there, you just do it more than once. And then once you've got it established, the right chemical balance, which is normally like 1,000 to 1,200 parts per million, then you're done. You close it off and it runs. And then every 6 months or every year, you check it again and add some more, because what happens, fresh water, if this has leaks or they've changed something, it will actually wash some of the passivation away, so you have to repassivate things over time. Pot feeders come in 2.5 gallon and 5 gallon size. Some have filters in them, some don't. Open loops, on the other hand, are different. Now, open loops has a pump that sucks water from the cooling tower basin and pushes it through the condenser barrel, pumps it over the top of the tower. And we have chemicals that we put in to try to passivate this cooling tower. Now, what we put in, and different chemical companies do it differently, but most systems have at least a barrel for chemicals that actually are trying to keep it from scaling, scale inhibitor. And that's all different kinds of chemistry. That's all proprietary and secret. And then you have a biocide, normally, a biocide that goes in to try to keep the green stuff out of your tower. And there may be an acid tank to feed acid. And the reason for that is the more acid your chemical treatment, the faster it works, and the less chemistry you actually have to use. Because what happens inside the tower, it's normally really alkaline. And it gets too alkaline to start scaling. So we want to pull that alkaline level back to where it's not corrosive. We want to keep it a little right around 5 to 6. We want to keep it right in that range. And then we put chemistry, that scaling chemistry actually tries to protect the corrosion of the tower. And the way we do that, we normally have a chemical system that we have another pipe running between the pump, condenser pump, and it's actually measuring the TDS of the water. And we run that the system, these tanks, off that TDS. And I think I've got, here's a TDS meter. Feed and bleed systems is a normal way. There are other systems, but the normal one is a feed and bleed. Sorry about that. Say that quick 10 times. So what happens is when we see a high TDS in the water, then this meter actually opens a drain valve and drains some of the water. At the same time, the level fill on the tower will start filling the water, putting fresh water in, thus reducing the TDS of the water, total dissolved solids of the water. And that's how it keeps it chemical. And then the feed and bleed system is when this is in the bleed mode, it turns on the chemical pumps. And the chemical pumps are basically, these are the barrel drums, and these are normally 50-gallon barrels. And then we have chemical pumps. And these chemical pumps, you adjust the stroke or the speed of them to adjust how much chemistry they're going to put in while they're on. And this meter just turns them on and off when this bleed valve's on. So the idea, thinking is, which is pretty smart, is when we've got high TDS and we're bleeding, we're feeding water, which needs chemistry. So as long as it's feeding water, we're pumping chemistry in it. And these are all separately adjusted. And the chemical treatment contractor basically adjusts all this stuff. And the only thing the Achilles heel of this system is if their tanks are empty. That's a problem, because these tanks have to be filled manually, because one has passivation chemistry in it, one has biocide chemistry in it, and one has acid in it. And you can't autofill those, so they basically have to be filled. And if you have an empty tank, doesn't matter how good a system it has, if it doesn't have any chemistry, it ain't working. So that's basically chemical treatment on chilled water systems, or hot water systems for that matter. Piping system components. Now, these are the individual components on the piping systems. We have a dirt and air removal separators, strainers, automatic air vents, valves, expansion joints, makeup water systems. So first, let's talk about separators. Sediment removal separators. And these are designed in the piping to be centrifugal separators. So basically, as the water comes in, or whichever way it comes in, I don't remember, it comes in and it's centrifugal. So it swirls the water around and then it goes out, causing the heavier elements to drop out, which would be the dirt and scale, falls out to the bottom, and then you can discharge it, that scale getting out of the system. You can also, at this point, take air out this way and take debris out this way. It can be manual, or this could even be automated with a solenoid valve. You just automate it. Then they have strainer types. These are separators. This happens to be a dual strainer, which is a really good strainer, which means when you're in this mode, you're operating this strainer. When you want to clean this, you switch this over now and operate this strainer. You can open this one up because this valve in here separates them so there's not gut flow in them. And you can clean the strainer. Sediment air separators. We have these that are floor mounted, large, and they also do the same. Take the sediment out, take the air out the top. Then we have pipe strainers, and we have standard strainers that look like this. And the way a strainer works, it's just got a sieve here. And what happens is the water enters it like this and goes through the sieve to exit like this, and the solids stay behind because the strainer straps them. So what you do is you remove this plug and blow this out, and it blows all the garbage out of the strainer and put it back together. This way it goes. These are available from 1/2 inch to 8, 10, 12 inch big strainers. The big ones above 2.5 inch all look like this because they got flanges instead of like this, which is screwed connections. And these are always made of steel, not brass. Could be stainless steel, but medium, large size Y strainers. Basket strainers, which we just showed before, have this basket in there. You can pull that out. Then we have pump suction strainers. And these go on the inlet of a pump. Right here would be a pump. So as the flow comes down, these do two functions. One, they're a straightener. So they take and move the water from vertical to horizontal, and they have veins in here to straighten it. And then these also can have a suction strainer in it. So this one has a strainer right here. And what happens is the water comes down, flows into the strainer, and has a sieve, and the sieve catches it, and the water goes out. So this is called a suction strainer. And these work fairly well. I'm okay with these. The only problem is when you pipe up a gauge, you need to put it right here or right here, and not up here. The gauge can't go up in the pipe because we can't include this strainer in the pump direction. And then we have strainer sieves, which is kind of a big secret. I don't know why, but this data was hard for me to find. Standard size screens are 1/8 to 1/4 inch. And this is water and this is steam. We also use steam. And this kind of tells you what the minimum sieves are. And this is the perforation size of the sieves. Now, what the thing is about this is when you have a pump has a volute on the impeller, and it sucks the water in and through velocity or centrifugal force pushes the water out those little volute holes. So your strainer must be smaller than those holes. If you put a strainer that has bigger holes in those volutes, the pump will get clogged. So like if you have a pump that has 1/4 inch holes in the impeller where the water leaves, it could be square holes. You need to have probably a 3/16 sieve, and this chart tells you what that needs to be. So, and now it doesn't mean that now, they make sieves way down to a real small sieve size, and you don't want to put those on a pump inlet. You want at the pump inlet, you want the biggest sieve that's going to protect the pump. Because you don't care if small things go through, they'll go right through a pump. So let them go through. And on a coil, you want to size the strainer to protect the tube. So if you have a coil with a 1-inch tube, you really don't even need a strainer. But if you have a coil that has a 3/8 inch tubes, you definitely need to have a strainer on that so the scale and stuff doesn't build up in that coil. But again, the coil strainers can be smaller than the ones on the pumps. Startup sieves, okay, so the main strainers in a system might have two sieves. They'll have the normal sieve, which might be an 1/8 to 1/4, and they might have a startup sieve that's much, much smaller. Inside it, it'll just lay right inside of those sieve. And what it's intended is to help the contractor, when he's starting up the system, get all those fines out of the system. However, they're not intended to stay. As soon as he's got it clean, he's supposed to remove those and take them out, because the system won't run with those in there. They're too small. They'll clog really easily and stop flow. So, first thing we did as a balance contractor is ask the contractor, did you remove the startup sieves? And if you get the deer in the headlight response, what's a startup sieve? You need to go make sure they've taken them out. It's really important. All right, here's some air vents, manual air vents or manual drains. Basically, they're a valve with a hose fitting on the end of it, and you use those to vent the air of the system, and we have to manually vent it and sometimes manually drain it. If you're working on a piping system and it has some loops that go down and up, then you'll need to have a drain at the bottom of each one of those loops to be able to drain the water out of those loops when they need it. Air vents need to be at the top of all high loops, high piping, so we can vent any locked air in the system. Air bleed valves and piping high points, drain valves and low points. We have automatic air vents, and these vents are designed to be at high points of the system, and they have a float valve in there. And anytime air enters it, the float bobbles and lets it escape. And the only neat things about these, they work all the time, very important, but this needs to be piped to the drain. If you don't, people are going to get wet. It just spits out water every once in a while. So you have to make sure those are piped to the drain. Now valves, there's all kinds of valves. Shut-off valves. Ball valves are most important, are very popular today because they're cheap and move a lot of water. Ball valves. Plug valves. Plug valve is the ball valve of the past. It basically had a block that rotated, and the block rotated closed the ports off. Still a very good valve, but it's a little more expensive than a ball valve. We have gate valves, and we have two kinds. We have a rising stem and a non-rising stem. In a non-rising stem valve, the gate rides up on the stem. You turn it, and it rides up on the threads on the stem. On a rising stem, it actually, you can see it rise right up out of the handle. This one never goes beyond the handle, but this one does. And these are big valves, normally used on utility, not so much for chill water and hot water systems, because of the way the packing is, and these are not as easy as the other kind of valves we have. Butterfly valves, so we've replaced these with ball valves and butterfly valves. Butterfly valves basically have a wafer, and when you open them, the wafer turns. So they're 90-degree valve. They rotate 90 degrees. Most of them come what's called bubble tight, so they'll have a rubber seat in here that it seals up against to get it to be bubble tight. In other words, it'll actually stop flow. They also make them that are not bubble tight, that are just a piece of steel up against a piece of steel, so they leak. You can't use them to shut off tight flow. They also make them in lug body type or wafer type. Now this is a modified wafer type. They make them just plain wafer, no bolt holes at all, and they just fit between two flanges. But then they also have these where you can actually bolt the flange. These have threads in them, so you basically thread a stud in this way and a stud on the other side, so you can actually take a flange off and it stays leak tight. These are what you need to use on chillers and boilers. Things you want to take apart and not have to dump the water in the system. You need to have a lug body valve. So that's the two differences in those valves. Different kinds of operators. You can have lever handle operators or gear turning operators. Check valves. Check valves are designed to only let water go one direction. So like this check valve here, you see it's got an arrow on it. It lets water go this direction. If water tries to come this way, this valve has a check gate that closes. And those check valves are used on all pumps or anywhere else you want to stop flow. That's a swing check. This is a spring butterfly check, so it has two wafers that come out together, and they have a spring that forces them open like this. So when water flows this way, it pushes them closed, and that's called a spring check, and we use that on a lot of pumps in HVAC. Pressure reducing valves. On makeup water, we normally need to limit the amount of water, pressure of the water, so it goes through there. And so we use these, and you'll show this on the system videos. We use this to limit the pressure on the incoming water. Pressure relief valves could be on our hot water system, on our boilers, to make sure they don't get overpressured. And of course, these valves have a spring set up in here, and when it gets hot, overpressure pushes against the spring and lets the water out. When it goes down, it closes automatically. Auto flow control valves. These are valves we used in coils to be automatic balancing. So what they do is they have a bunch of spring actuated little cups in here, and as the water pushes it one way or the other, you get more or less flow. So if this cup is all the way in, then we have a lot of flow because we have a lot of area. It's all the way out, we have small flow. These are called automatic balance valves. Then we have balance valve, manual balance valves, which basically have an orifice that you can read, and you have a knob where you can adjust the flow. And the balance guys, of course, use these on all the coils and places where balance is required. Coil kit valves is a kind of a device created by valve manufacturers to sell more stuff. And basically they have two shutoff valves, and they have a balance valve built in and a strainer built in, plus some braided hoses to hook the coils. Now on small coils, say up to 1 inch, these are very handy, and the reason these have this flex hoses, because now it becomes much more efficient for the contractor. His piping mains do not have to be, his branches don't have to be exactly in the right place. You know, if you're doing hard piping, you come out here and you're off by an inch, now you got to put 2 elbows and offset, a whole bunch of work. With these, if you're off an inch, no problem, just hook them up. And that's why we have those hoses. Control valves, okay, all kinds of control valves. The very best valve is called a globe valve. And the reason is it's the most proportional valve we have. So what happens if you have a linear control valve, it means that if you're looking at the chart, it's proportional linear response. To if you want it 50% open, then the valve will actually flow 50% flow. On other valves, that's not the case. So this is a globe valve. It's got a globe sitting. This is a parabolic seat. So basically, when this rises up, it is in a parabolic fashion, giving you that equal flow. Globe valves are 1/2 to 6 inch shut-off valve seat. They have one shut-off valve seat. So there's two-way valves. This is a globe valve. Then we have ball valves, 1/2 inch to 3 inch. You can get an industrial ball valve bigger, but man, they're super expensive. So you want to stay this way. And of course, this has a ball in it that's got drilled, and as soon as you turn it, it closes off. So that's a ball valve. We have a 3-way mixing valves, and these are where we take water from 2 sources and we mix them together. So we got water coming up this way, and we got water coming up this way, and this valve will allow these waters to mix. As these 2 seats, this doesn't have a seat down here, it moves up, and it allows it to flow through. They're 1/2 inch to 6 inch. They have one. They look like they have 2-way seats, but they don't. One's a guide vane, one's a seat. So they're mixing. They're always mixing water. They're never shut off tight. That's not their intention. I mean, they shut off tight right in this one mode. They won't shut off to the drain. And this would make sense because you want it to shut off the supply water or the water from the coil. You don't want it shutting off the right. So this will only shut off this stream. These 2 streams, it won't shut off this stream. So you have ball valves, 1/2 inch to 3 inch, 3-way ball valves, somewhat confusing, but they have a drill port that looks like one drilled all the way through, one halfway. And these are the different modes of operation of that 3-way ball valve. We have 3-way diverting valves. Now, this gets a lot of guys confused because there are 3-way valves both in mixing and diverting valves. And in air conditioning, we never, ever need a diverting valve unless you have a bypass chiller on a system where you're going to run the water to a chiller, then take it away and run it to another chiller. Then you would need these kind of valves, diverting valves. The people get confused. Engineers get confused on it. Diverting valves have 2 seats and are more expensive, but we never need them in air conditioning because we're always in a mixing condition. And the way to tell is a mixing needs to always be downstream of the coil. A diverting valve needs to be upstream because it's diverting water away from it. So we wouldn't use them. These basically look like exactly like the other one, but they don't because these have 2 seats. Water comes in, goes this way, or water goes this way. So they're a different kind of valve, and they have 2 complete seats. Ball valves, 3-way. diverting, and these can also be diverting. It's just run differently. The ball valve doesn't care, because it's always got the same seat. And then butterfly control valves. Now, butterfly valves have this wafer in this frame, and what the deal is, this 60 degrees is telling you that between 60 degrees and 90 degrees full open, no control. Nothing happens. It all happens between 60 degrees and closed. So when we're doing a butterfly valve and trying to use it for control, mostly these are shut-off valves. You're trying to use a control, we only control to this 60-degree angle. Because if you try to control the 90 degree, you just lost 30% of the action of that valve. So you need to make 60% full open. You can have a characterized fishtail valve, which puts a little wafer, got a funny little thing that looks like a fishtail on here that allows us to be more linear. This is a terribly not a linear valve. It's a much different position on it. So these fishtail valves or industrial valves are really expensive, but you can use them, but we almost never do. So pipe expansion joints. So we get, this is a poor man's expansion joint. It's just a bunch of flexible pipe couplings hooked together with little short pieces of pipe. But it does work. It allows expansion, contraction, and allows movement laterally. The expansion loop, this is a loop that does this way, and it allows these flex connections allow this pipe to move. You put an anchor here, and they can move either way. A pipe expansion mechanical fitting, whereas you anchor this pipe, and this pipe is allowed to move in and out. And this is a bellows, a metal bellows, so they're watertight, not a problem. But they will move this length, whatever the compression is of that bellows, they'll do this, and this will move back and forth. Flex connection couplings, which is normally at pieces of equipment, has a flex. This is a rubber with a metal braid on the outside. You can have a bellows, which is a metal bellows on the outside of a pipe, or you can have a rubber flex connection. These are always used, these two are used at pumps normally. And these have retainers, and these may also have retainers. And retainers are designed to make sure it doesn't flex more than this coupling can actually take. So it might be only, a half-inch flex or a quarter-inch flex. And that's why when you get on a job site, you may notice these are not tightened. They're tightened. They're just designed to be a stop point for this flex connection. Makeup water systems. We have reduced pressure backflow preventers, which for small pipe equipment connections, large pipe connections, do either one. So this basically has what we call a reduced pressure fitting. As if water comes in, we have a pressure reducing valve, and then we have a zero pressure here and another pressure reducing valve. If the pressure is over pressure, it'll run out this system right here. So those are the large, and then there's coming a big system like this. So this could be on the inner of a building. This may be the entrance to a water feeding a cooling tower. So it can be different ones. And then of course we have glycol feeders. Now, glycol feeders are designed to keep the glycol mix in this tank. So if you have a system that needs a 60% glycol, then you have this is mixed with water and glycol to that 60% mix. This pump pumps out to the piping system. We have a pressure sensor on it that says we want this making up, say if we run a system with 18 psi pressure, system pressure, we put this a little bit higher so this pump can pump it in to the system, and we watch that pressure to tell when it's low on water. So if it's an 18 psi pressure and this drops down to 16, it starts pumping some water in there. But the reason we don't have these connected to the water system is because of the water in the chill water system leaks, and it gets filled up with fresh water, and the operators don't know it, it'll freeze. So what happens here is we make them keep eye on this tank to make sure, because we never allow it to automatic fill. It's always filled automatically from this tank. Made it through this system. Sorry about this being a long video, but tried to get it all into one. So I hope this was helpful to you. Don't forget to become a subscriber. We really like to have you be a member of our technical group here. Thanks for watching. Have a great day. I'll catch you on the next one.